Welcome to Lecture 15. This is the series end for the PhDAI730 at University of the Cumberlands at Kentucky. Artificial Intelligence and NLP utilizing advanced statistics. Statistics is the one word which I always stumble upon. This is Professor T. Fareed Muhammad. And let's continue. So this week we will delve into the advanced techniques of natural language processing and statistical methods for text analysis, with a particular emphasis on topic models. Those sophisticated methods are indispensable in the realm of data science as they enable us to distill vast amounts of textual data into meaningful insights. By leveraging natural language processing, we can automate the extraction of sentiments, themes, and patterns from text, which is crucial for applications such as sentiment analysis, where understanding the emotional tone behind words can inform decision-making processes. Document classification benefits significantly from these techniques as they allow for the categorization of documents based on their content, facilitating efficient information management and retrieval systems. Topic models such as latent direct allocation or LDA are at the forefront of these advanced techniques, providing a robust framework for uncovering the underlying thematic structure in large collections of documents. By identifying topics within a corpus, these models enable us to summarize and interpret textual data in a way that reveals hidden patterns and relationships. This capability is not only essential for information retrieval, where the goal is to find relevant documents in response to a user query, but also for a wide range of applications, including market research, social media analysis, and academic research. Through the application of these advanced natural language processing techniques and statistical methods, we can transform unstructured text data into actionable insights, thereby enhancing our ability to make data-driven decisions. Natural language processing is a branch of artificial intelligence that enables computers to understand, interpret, and generate human language in a meaningful and useful way. Virtual assistants like Siri and Alexa use NLP to parse spoken commands and return contextually relevant responses in real time. To what extent, in your opinion, can current natural language processing models accurately interpret ambiguous or culturally specific language across diverse linguistic communities? Now, this is an area that I would strongly suggest you to conduct research on and get an understanding, because natural language processing has introduced natural language understanding and natural language generation as the next level of work that we are dealing in the arena of generative artificial intelligence or large language models. Text analysis. Now let's look at this topic in a little bit more depth. So text analysis is a computational process of deriving structured, actionable information from unstructured textual data using statistical and linguistic methods. Financial institutions apply text analysis to earnings call transcripts to predict stock price movements based on executive language patterns. So text analysis is the process of using computer programs and statistical methods to examine large amounts of written material and extract meaningful information from it. Instead of person manually reading through thousands of documents, text analysis allows machines to automatically detect patterns, themes, sentiments, and relationships hidden within the text. Techniques such as tokenization, TF-IDF, we'll discuss that in length in the coming slides, and topic modeling as well, work together to break down language into measurable components, making it possible to draw conclusions from data that would otherwise be too large and complex for any individual to process. In essence, text analysis bridges the gap between human language and computer understanding, turning words on a page into data points that can be studied, compared, and acted upon. A compelling real-world example of text analysis is in action is the investigation of the Enron email dataset. When the American energy company Enron collapsed in 2001 following one of the largest corporate fraud scandals in history, investigators were left with over 600,000 internal emails exchanged between employees and executives. Reading through all of them manually would have taken years, but by applying text analysis techniques, researchers were able to quickly identify recurring topics, trace suspicious communication patterns, and pinpoint the key individuals involved in the cover-up. For instance, topic modeling revealed clusters of emails discussing financial terms like mark-to-market accounting and special purpose entities, language closely tied to the fraudulent practices at the heart of the scandal. Sentiment analysis further showed a sharp shift in the emotional tone of communications as the company approached its collapse, with anxiety and urgency becoming increasingly dominant. The case powerfully illustrates how text analysis can turn a mountain of unstructured data into a clear, navigable map of human behavior and organizational wrongdoings. Corpus is a large, structured collection of texts used as the foundational dataset for training, testing, and applying NLP and text analysis models. The Google Books corpus is used by researchers to study linguistic and cultural trends over centuries through large-scale word frequency analysis. Here is a research question for you that you can go and conduct study in IEEE Explore or Google Scholar, that how does corpus size and domain specificity interact to influence the generalizability of NLP models trained on them. We just have discussed the Enron emails. That was a big corpus where people have found the details as I discussed earlier. Tokenization is a process of breaking stream to text into individual units such as words, phrases, or sentences called tokens, which serve as the basic input units for NLP models. Search engines tokenize user queries to match individual terms against indexed documents, improving retrieval precision and recall. Let's look into this with an example in more depth. Tokenization is one of the most fundamental steps in the text analysis process, and it refers to the method of breaking down a large piece of text into smaller, manageable units called tokens. These tokens can be individual words, punctuation marks, or even entire sentences. Depending on the level of analysis required, think of it like taking a long, continuous sentence and carefully cutting it into separate pieces so that the computer can examine each part on its own. Without tokenization, a machine would struggle to make sense of language because it would see an entire paragraph as one long, unbroken string of characters rather than a collection of meaningful units. By converting text into tokens, NLP systems can begin to count word frequencies, identify important terms, compare documents, and feed the data into more advanced models for deeper analysis. A practical way to understand tokenization is to consider how it would be applied to a simple news headline such as the Federal Reserve raised interest rates for the third time this year. When tokenized at the word level, this sentence is split into individual units such as the, Federal Reserve raised interest rates for the third time this year. I have given a pause between every single word that I enunciated, each of which becomes a separate data point for the computer to work with. From here, common words like the, for, and this might be removed as stop words, leaving behind the more meaningful terms such as Federal Reserve, raised interest rates, and third time. In the large data set of thousands of such news articles, tokenization makes it possible to track how frequently terms like interest rates or inflation appear over time, helping analysts detect trend in financial journalism. Without this seemingly simple first step, none of the more sophisticated text analysis techniques that follow would be possible, making tokenization the essential foundation upon which all of NLP is built. So we'll continue learning on text processing. Stop word removal is a text pre-processing step in which commonly occurring words such as the, is, and are filtered out because they carry little semantic meaning in most analysis, as we just discussed earlier. In legal document review, stop word removal reduces noise and allow models to focus on substantive terminology relevant to case categorization. So here is a research question for you to conduct study at using Google Scholar. Under what analytical conditions does retaining stop words improve rather than degrade model performance in NLP tasks? So conduct a research on that to understand this area in a little bit more depth. TF-IDF, term frequency, inverse document frequency, is a statistical measure that evaluates how important a word is to a document relevant to a collection of documents, balancing frequency with rarity. News aggregates use TF-IDF to rank and recommend articles by identifying the most distinctive terms in each piece relative to the entire article database. Now let's look into this in a little bit more depth. So TF-IDF is a statistical method used in text analysis to determine how important a particular word is to a specific document within a larger collection of documents. The core idea behind TF-IDF elegantly simple. A word is considered significant not just because it appears frequently in one document, but because it appears frequently in that document while being relatively rare across all other documents in the collection. The term frequency part measures how often a word shows up in a single document, while the inverse document frequency part penalizes the words that appear in almost every document, since common words like the or said carry very little distinguishing value. By multiplying these two measurements together, TF-IDF produces a score for each word that reflects its true importance and techniques within the context of a specific document, making it one of the most widely used and reliable tools for identifying the words that actually define differentiate a piece of text. A helpful way to see TF-IDF at work is to imagine a collection of 1,000 restaurant reviews. Words like food, restaurant, and service would appear in nearly every single review. So despite their high frequency, TF-IDF would assign them a very low score because they do not help distinguish one review from another. However, the word like truffle or Michelin might appear frequently in just a handful of reviews. TF-IDF would reward these words with a high score because they are both locally frequent and globally rare, meaning they tell us something specific and meaningful about those particular reviews. A restaurant owner analyzing this dataset could use TF-IDF scores to quickly identify which dishes, experiences, or qualities are being highlighted in positive versus negative reviews without having to read each one individually. This example demonstrates why TF-IDF is so powerful in practice. It cuts through the noise of everyday language and surfaces the words that truly matter, giving analysts a precise and efficient way to understand what makes each document in a large collection unique and informative. Sentiment analysis is an NLP technique used to identify and extract subjective information such as opinions, emotions, and attitudes from textual data. Brands monitor social media platforms using sentiment analysis to assess public's reaction to product launches and adjust marketing strategies accordingly. How accurately can sentiment analysis models detect sarcasm and irony? And what linguistic features most reliably signal these forms of non-literal expression? Now, that's a question you can conduct a research on. Document classification is the task of automatically assessing predefined categories or labels to textual documents based on their content using machine learning algorithms. Email service providers use document classification to distinguish spam and legitimate messages, routing them into appropriate folders with high accuracy. Now let's look into this with an example. Document classification is the process of automatically assigning predefined categories or labels to pieces of text based on their content using machine learning algorithms that have been trained to recognize patterns associated with each category rather than having a human manually sort through thousands of documents and decide where each one belongs. Document classification systems learn from examples and apply that knowledge to new unseen texts or at remarkable speed and scale. The process typically begins after functional steps like tokenization, and TF-IDF have transformed raw text into numerical features that a machine learning model can understand, at which point the model analyzes those features and makes a judgment about which category and document the document most closely resembles. Document classification can be as straightforward as sorting emails into spam and not spam, or as complex as categorizing thousands of legal briefs, medical records, or news articles into dozens of highly specific thematic groups. What makes it such a powerful tool is its ability to apply consistent data-driven logic across enormous volumes of text in a fraction of the time it would take any human team to accomplish the same task. A vivid real-world example of document classification can be found in the way major news organizations manage their digital content archives. Consider the media company like the New York Times or Wall Street Journal, which publishes hundreds of the articles every single day across topics ranging from politics and economics to sports and entertainment. Rather than employing a team of editors to manually tag each article with the appropriate section label, a document classification model can be trained on thousands of previously labeled articles to learn the distinguishing language patterns associated with each category. The model quickly learns that articles containing the word like Congress, election, and legislation most likely belong to the politics section, while articles featuring like earnings, stocks, and merger are more characteristics of the business selection. Once deployed, this system can instantly classify every new article published, routing it to the correct section of the website, recommending it to the right readers, and making it easily searchable in the archive. This example highlights how document classification does not merely save time, it actively improves the organization, accessibility, and user experience of large information systems, making it an indispensable technique in any environment where text is produced and consumed at a high volume. Topic modeling, it's a big topic in itself. A topic model is an unsupervised statistical model that identifies abstract topics, clusters of co-occurring words within a large collection of documents without requiring predefined labels. Academic publishers use topic models to automatically tag research papers with thematic categories, improving discoverability and indexing efficiency. How should the number of topics in a topic model be determined, and what evaluation matrix best captures human interpretable coherence? That's a question I would suggest you look into. Latent directlet allocation (LDA) is a generative probabilistic topic model that assumes each document is a mixture of topics and each topic is a mixture of words drawn from directlet distributions. Policy analysts apply LDA to large archives of government documents to trace how public health discourse has evolved over decades of legislative debate. BOW, the bag of words model. The BOW model is a text representation method that describes a document as an unordered collection of word frequencies, disregarding grammar and word order. Spam filters use bag of words representations to train classifiers that identify unwanted email based on the presence and frequency of characteristic terms. Word embeddings are dense, continuous vector representation of words that capture sentiment relationships based on their contextual usage across large text corpora. We have discussed the corpus before. E-commerce platforms use word embeddings to power recommendation engines that suggest products based on the semantic similarity of search queries and product descriptions. The research question for you to ponder upon is, to what degree do word embeddings trained on general corpora transfers effectively to specialized domains such as biomedical or large text? LSA, latent semantic analysis, is a technique that applies singular value decomposition to a term document matrix to uncover latent semantic relationships between terms and documents. Educational technology platforms use LSA to assess student essay quality by measuring the semantic similarity between student responses and expert authored model answers. Directlet distribution, it's also known as DD, is a family of continuous multivariate probability distributions using in LDA as a prior over topic mixtures in documents and word mixture in topics. Content platforms use directlet based priors in LDA to model the natural skewness of topic distributions, reflecting that most documents focus on a small number of themes. How sensitive are LDA's outputs to the choice of directlet hyperparameters, and what automatic tuning strategies yield the most stable results? That's a question that I would suggest you to look into. Perplexity, not the company. Perplexity is a statistical measure used to evaluate language and topic models, quantifying how well a probability model predicts a sample Lower perplexity indicates better predictive performance. Natural language processing researchers use perplexity to compare competing topic models on held out test corpora to select the configuration that generalizes best to unseen documents. NER, named entity recognition, is an NLP substack or subtask that locates and classifies named entities in text such as people, organizations, locations, and dates into predefined categories. Investigative journalists use NER to automatically extract the names of individuals, companies, and locations from leaked document datasets for rapid analysis. So here's a research question for you to ponder upon. How can NER models be made more robust to emerging entities such as newly coined brand names or public figures that were absent from training data? PGM. PGM is technically probabilistic graphical models. These are a class of statistical models that use graphs to represent the conditional dependencies between random variables, providing a framework for reasoning under uncertainty in complex domains. Medical informatics teams use probabilistic graphical models to extract structured clinical information from unstructured physician notes for electronic health record population. Natural language processing transforms unstructured text into structured insight. Through foundational techniques such as tokenization, TF-IDF, and bag of words representations, raw language is converted into formats that machines can analyze, classify, and interpret at scale. Sentiment analysis and document classification are core applied tasks. These methods enable organizations to automatically detect emotional tone, categorize content, and manage large volumes of text-based information efficiently and accurately. Topic models, especially LDA, reveal hidden thematic structures as we discussed earlier. By modeling documents as mixtures of topics and topics as mixtures of words, LDA uncovers latent patterns with corpora without requiring any predefined labels or categories. Statistical rigor underpins model evaluation and inference. Concepts such as the DD-Gibbs sampling, perplexity, and dynamic topic modeling ensure that conclusions drawn from the text data are probabilistically sound and empirically validated. Real world impact spans every major domain from healthcare and legal research to market analysis and social media monitoring. Advanced natural language processing techniques convert unstructured textual data into actionable, decision ready insights that drive measurable outcomes. Happy learning.